So, new page. Let's give me some lines to write on. Those are too big. How about these? All right, perfect. All right, so section 8.1, linear systems. Yes. So just some preliminary theory, basically notation more than anything else. So consider the following system where I've got n dependent variables, x1 through xn, and one independent variable. And I'm writing the first derivative, dx1 dt, is a linear function of all the other dependent variables and perhaps one function of the independent variables. So I'm going to write it as a linear system. A11 of t times x1 plus A12 of t times x2 plus dot 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 plus all the way out to A1n of t xn plus f1 of t. It's my first equation in my system. Notice the linearity of it. It is linear in x. It's linear with respect to the dependent variables. And it's a first order differential equation because you got first derivatives. The coefficients now, instead of necessarily being constants in general, they could also be dependent on t. We'll spend almost all of our time talking about ones where the A11 through A1n's are just constants. But the theory can be expanded to handle where these could be functions of t, just not of x. And then you've got a dx2 dt, following the same pattern, but now a21 of t x1 plus a22 t x2 plus a2n of t x2 plus f2 of t. Dot, dot, dot. dxn dt is equal to x, nope, an1 of t x1 plus an2 of t x2 plus dot 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 plus ann of t xn I wrote an x2 here. This should have been an n right there.
Should that f? Oh, it is
Fn of t. So I have n squared coefficients for my x's, and then I've got n of these f functions here. All right, so this is what we call a first order linear system of ODEs, ordinary differential equation. All right, the dependent variables are x1, x2, all the way out to xn. The independent variable is t. And you can think of the f1 through fn as the right-hand side of our higher order differential equations that we looked at in chapter 4. So that if all of these were 0, all you would have is the dependent variables on the right-hand side and their coefficients. You wouldn't have something extra depending on just t. So that's the homogeneous case, okay? If f sub I of t is identically 0 for all I from 1 to n, the system is called homogeneous. Make sense? Okay, the nice thing about this is that when we think of this as a system, we've already, in previous coursework, developed some necessary tools, some very useful tools for, one, writing this in a much more condensed way, right? If I want to think of this as a matrix system, I can do so using a matrix form or matrix notation. What I do is I let capital X be a vector function, x1 of t, x2 of t, all the way down to xn of t. They're the dependent variables, just think of that. And think of A as a matrix function aij of t that's n by n. Those that took linear algebra with me last semester will recognize that notation. It's just me in a condensed form writing down what I would normally have written, and you don't have to write this, but as A11, A12, dot, 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 A1n, A21, A22, dot, 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 A2n, down here to AN1, AN2, dot, 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 ANN, right? That's my way of writing that, where I and J represent the ijth element. I is the row, J is the column, and its dimensions n by n. So just denote these as these functions that are up here inside that system. And last of all, capital F is f1 of t all the way down to fn of t. It's another column vector. Now I take advantage of a couple of notational facts that I'm assuming you're familiar with. If I were to write down x, which is now a vector function, in Calculus 3 we introduced just the notation of taking a derivative of a vector function. Just means element-wise, take the derivative of each of its component functions. And then from linear algebra, we use the vector, or the matrix vector definition for multiplication, right? A times x. When you take a matrix times a vector, you do row times column, right? And add it up. So you go across the row and down the column and put the plus sign in there, which is exactly where we get like that first equation up here. Because if you take A11 times x1 plus A12 times x2, I'm going across this row and down this column to get the right-hand side, but I also have plus capital F. So this, using these as my notation, says exactly the same thing as the system I wrote first. I can just write it like that, okay? And then the homogeneous case is just x prime equals ax. And just, again, one more time, keep in mind that A can be a matrix function. So it can, all of its elements can have t's in them. But we will spend most of our time looking at ones that don't.
Why are you double barring the X? Is that just a?
That's so that you can tell it's a
Capital.
capital.
Okay.
Yeah. I would do that with my F too, but it looks like an E. I mean, I could put little hoochies on it right there, serifs.
I think it's fine.
But you can tell a capital F from a lowercase f, so it's not a big deal. But X and X are too close, so it's just a habit that I've always gotten into. X, Y, and Z. When I make capitals, I always put little serif for feet on them. But that's all. And some books, by the way, since F and X are vectors, you may also see X bar prime equals capital A, X bar equals, or sorry, plus F bar. Right, we call them vectors, representing them as the bar notation instead of as actual matrices that just have a one dimension that's one. It doesn't matter.
Many books to learn
Lots of different ways around here. You'll see them. dx dt is equal to 3x plus 4y. dy dt is equal to 5x minus 7y. I'm just going to write in matrix form. So, if I let x be the vector x, y, then matrix form looks like this. X prime is 3, 4, 5, negative 7 times x. Easy. If dx dt is 6x plus y plus z plus t, and dy dt is 8x plus 7y minus z plus 10t, and dz dt is 2x plus 9y minus z plus 6t.
Is it supposed to say 8x equals 7x?
That's a y.
Oh, okay.
Where x of 0 is 0, y of 0 is negative 2, and z of 0 is 4. All right, so write in matrix form. Again, just making sure you see where the different pieces come from. When we start working with these things in great detail, we're going to be identifying the coefficient matrix and then working with that to find its eigenvalues and eigenvectors and such. Okay, so if we let capital X be x, y, and z, I would write it as, and your matrix is 6, 1, 1, 8, 7, negative 1, 2, 9, negative 1. And notice how I put all of this stuff, since it doesn't depend on the x, y, and z, off in its own vector. T, 10t, and 6t. Yep, yep. In this case, it's not that common for your forcing functions to be as simple as this, but yes, you can do that. Okay, so solutions to systems. Instead of really writing anything out here, I think it should be pretty obvious to you what it means to do this. If I told you that we have the system x prime equals 1, 3, 5, 3, capital X. And I ask you to verify that x1, which is 1, negative 1, the vector, times e to the minus 2t, and x2, which is 3, 5, times e to the 6t, are solutions. Let's think through what that means for me to verify. First of all, just recognize that this is the same as e to the minus 2t and negative e to the minus 2t as a vector. You see that? Mm-hmm. Why that's true? I'm just multiplying in that function, right? Mm-hmm. So what I'm really thinking of is if x was like the vector xy from up here in my example that I was doing up here, then I'm thinking of this as x of t is e to the minus 2t and y of t is negative e to the minus 2t. And notice how writing it this way is just using vector notation to write down that I've got two solutions. I've got the solution to each dependent variable, right? But I can write it in this vector form. And in fact, it's even better in the vector form for this particular question being asked, because I want to plug that into the original equation to verify. Okay, so I don't actually have to use this information. I just want you to see that when I've given it to you in this form, it's still a way of writing down that I've got the solution to the x component and the solution to the y component. But now I've written it like this, and what I want to do is I want to verify that it satisfies this, which means do the same thing we did in chapter 1, which is plug it in on the left-hand side, plug it on the right-hand side, and see that you get the same thing. On the left-hand side, I've got to take the derivative. On the right-hand side, I've got to do a matrix multiplication. Just check that I get the same answer both times when I do that. So let's do that with x1. x1 prime is the derivative of either this that I've got written in blue or this that I've got written in red. Let's just find the derivative. It doesn't matter which one you do. By the way, if you do the derivative of up here, just realize that this minus 1 minus 1 is like a constant out front, and you can just take the derivative of the function, which is the negative 2 e to the minus 2, and then multiply the minus 2 in. Or you can just take the derivative of this. Either way, you get minus 2 e to the minus 2t and 2 e to the minus 2t. Agreed? And now what is A times x1? Where this right here, of course, is A. Your A is 1, 3, 5, 3 times x1, which is 1, negative 1 times e to the minus 2t. Remember your matrix vector multiplication across this row down here. So 1 times 1 minus 3 is a negative 2. 5 times 1 minus 3 is a positive 2. Which is equal to negative 2e to the minus 2t and 2e to the minus 2t. I just went ahead and multiplied it in so I could see that those are the same. So that's how you verify that it is in fact a solution. First, I took my x1 and I took the derivative of it. Second, I took my x1 and plugged it in on the right-hand side and saw that I got the same thing on both sides. Okay? I'm going to do x2 almost the same way. In fact, I'm going to skip the step of multiplying this in. I'm just going to take the derivative of this, right? So that's a 3, 5, just sticks around, times, and what's the derivative of e to the 6t? Okay? Which gives me 18 and 30 e to the 6t. If I do a times x2, that's 1, 3, 5, 3 times 3, 5 e to the 6t, which gives me 18 and 30 e to the 6t. Which, by the way, gives us some insight. If you think about what I just saw, there's something very interesting happening right here. This number right here is the same as this number right there, obviously, right? So think of this as, I'll call that lambda, right? This is like lambda times e to the lambda t times some vector, call it x. In fact, that should be, I'm going to write all this in a different color so it doesn't interfere with what I'm doing here. And you don't have to write this down necessarily because I'm going to write this information when we derive the solution in chapter or section 2. But I've got a lambda t, e to the lambda t. I've got a lambda here, and I've got an x. Okay? Or if I just rearrange this, I've got basically a lambda x e to the lambda t is the derivative. Right? Over here, what I've got is that same x. I've got a e to the lambda t, and I've got a. A x e to the lambda t. Where x now is not an unknown, it's some actual vector. Right? It's an actual vector. That's why I use the x bar instead of the capital X notation. But notice, in order for this to be a solution, what I want is I want this to match this. I want to find a vector x so that a times x is the same thing as some number times x. And where have you seen that before? That's the eigen equation, right? Eigenvector, eigenvalue equation. Finding a lambda and x that satisfies this is finding the eigenvalue and eigenvector that goes with it. If you find that, then the vector times e to the eigenvalue t is going to be a solution. That right there is the reason why first order linear systems are so tightly connected to eigenvalues and eigenvectors that I've talked about before. Okay? All right. There's that. A couple of notes that I want to throw in here. I'm skipping over important information that I'm not even going to give you about existence and uniqueness of solutions. I do want to throw in something called the superposition principle. Turns out the superposition principle holds. What that means is that if x1 and x2 are solutions in the homogeneous system, then x equals c1 times x1 plus c2 times x2 is also a solution to the homogeneous system. So just as before, solving the homogeneous system means finding, M-E-A-N-S, finding n linearly independent solutions x1 to xn and writing your general solution as x equals c1 x1 plus c2 x2 to cn xn. Okay, and checking if they're linearly independent is actually using a Wronskian, but the Wronskian for systems actually don't even need derivatives. I'll show you that at the beginning of class next time, but we'll start on Thursday solving some systems. Where things get complicated is in the lots of different types of cases where you have complex versus real eigenvalues, when a single eigenvalue has multiplicity, when eigenvalues don't have have multiplicity, but then they have multiple eigenvectors that go with them. Sometimes an eigenvalue can be repeated, but only have one eigenvector that goes with it. There's lots of different cases for eigenvalues and eigenvectors. So we're going to start class on Thursday with remembering how to find eigenvalues and eigenvectors. I thought I was going to post a video, but I decided I'm just going to take class time to review just the essentials, because all my videos have a lot of background information that at this point you either expected to know or I actually don't care if you know. I just want you to be able to find an eigenvalue and an eigenvectors. Okay? Done. Kristen.